Okay, good morning. So the plan for today is just to continue with Chapter 7 factoring. Again, we're moving into some of the more difficult material now in Section 7.2 and 7.3. So this is definitely where it'll be really beneficial to read ahead a little bit. It would be beneficial if you read a little bit through 7.3, looked a little bit through that section already before today's class. But if you haven't, make sure to kind of allot a few days to work through the homework, chip away at it little by little. Don't try to leave it all till one day and then try to rush through it all at once. Sometimes these problems can be a little more challenging. Sometimes the topics can be a little more challenging. So giving yourself a little bit of extra time to maybe come back to a problem that you found challenging, like a day or two later, that can be really helpful. So, but today we're going to continue on with factoring general binomials, or sorry, trinomials, general quadratics, second order equations. The quote of the day today is from a movie called The Truman Show. I think it came out maybe in the early 2000s, and it starred Jim Carrey. And basically the premise of the show is that this guy Truman, he was like, from when he was born, he was brought up on this huge movie set that he doesn't know is a movie set. And it's like this little village. All of the people that he interacts with are actors. There's cameras everywhere. And the whole point is that it's like a reality show about his life. So he's the only one that doesn't know that he's part of this massive production. So I mean, it explores a bunch of really interesting ideas and topics and so on. But the main producer, director, or whatever, this guy Christoph, he had a quote at one point that I thought was really interesting, where he says, "We accept the reality of the world with which we're presented. It's as simple as that." So basically, I think somebody was asking him, like, how doesn't he like know that he's part of this reality show? And this is basically his answer. And I think, you can take it at face value, and it just says something about, the plot device of the show or something, or explains why you should suspend disbelief a little bit. But I think these days, particularly, there's a lot of questions about education and the value of education and what the benefits of education are. And I actually see this as, kind of answering one of those questions in a sense. And of course, there are lots of maybe more tangible answers to, like, why should you get a college degree? There's return on investment. You make more money on average over your career. It opens up other opportunities. There might be a field that you really, really want to go into that requires a college degree, and you get, say, greater purpose or something out of that. So there are all those kind of answers, and I don't mean to push those aside with this answer, but I hope this answer complements those, because I don't think that it's just about return on investment or just about opening up a career field that you might not otherwise have. I think, what I really like about this is that each of us is presented with a certain point of view of the world, right? Our parents, our family, our folks, the neighborhood we grew up in, our friends. That group of people are going to present us with a certain reality of the world, and we tend to kind of accept that as how the world is. If we don't venture outside of that, kind of bubble, in somewhat of a literal sense, in the sense of the Truman Show, if we don't venture outside of that, well, we accept that as the reality, and that's that. And, we assume everybody else has that same reality. I think one of the benefits of education is, particularly college education, but also probably almost all education, is that it opens us up to the fact that there are different realities, that, somebody on the other side of the world, or maybe even, 10 minutes away from you, might have grown up with a setting that where they experienced a completely different set of circumstances that they're presented, and they have a completely different perspective of the reality of the world. And I think that, at the very least, can help us to realize there are many different perspectives on what the reality of the world is. especially today when things are so connected, where in a couple of seconds you can be talking with somebody on the other side of the world, or you're on Facebook and the comments that are on, or I don't even know if people go on Facebook anymore. I don't know if that's the cool thing anymore, but whatever, Instagram or whatever it may be, the comment threads could be one comment from somebody in the US, another comment from somebody from India, another comment from somebody in Canada, and somebody from China, like all communicating back and forth, right? We all have different realities that we've grown up with. So I think that's one of the huge benefits of education, is trying to show everybody an assortment of different realities, assortment of different backgrounds. And some folks will look at one reality and say, oh yeah, I'm in a sense like an expert in that. I've lived that, and somebody else might not have ever heard of that, and vice versa. So I think that's one of the really big benefits. And, ideally, I think that can help kind of humanize other folks, so that we're not saying, oh, that's other and this is reality. But hopefully we're all kind of seeing that we're all part of this. So as far as things like general education courses or liberal arts core or whatever you might call it, when the classes where somebody says, well, I'm going into this major, when am I ever going to use that idea? I think that this gives somewhat of an answer to that. And as an aside, I despise the answer, oh, it's like doing mental push-ups. Like that's one of the very common answers, but it's like, oh, you're exercising your mind or whatever. I don't know. I can't stand that answer, because it doesn't answer the question. It just pushes the question off to the side, right? There's lots of ways to do mental push-ups, and why do I have to take this course? It doesn't answer that question. But anyway, so that's the quote of the day for today. There's a lot of, if you watch movies or TV shows or whatever, a lot of times there's like the surface level interaction that you can just, turn off your brain and watch it and enjoy it. But in a lot of movies and a lot of TV shows, there's a lot of deep ideas and philosophy and so on. If you really think of it, like Breaking Bad is a really good example of that, or even South Park, like with the like funny, like kind of crude surface level interpretation, but there's usually a layer or two deeper of interpretation behind all of the crude language of the kids. Okay, so let's look at factoring trinomials of the form ax squared plus bx plus c, where a is not equal to 1. So we're trying to generalize from what we did last time. Last time we looked at factoring trinomials that looked like x squared plus bx plus c. We're looking at factoring things of this form where a was equal to 1, and we had a strategy for doing that. So my goal is to rewrite ax squared plus bx plus c as, say, dx plus m times ex plus n. And typically we're going to want de, m, and n to be whole numbers or integers. And note that if I multiply out dx plus m times ex plus n, this is what I end up with. So I do end up with, from that d and e, d times e is the coefficient of x squared, which allows me to match this term. Before, we just looked at factoring x squared plus bx plus c as x plus m times x plus n. In other words, where d and e were both 1, and that was the special case where a was also just 1. And we have two main methods here. The first method, which we'll start with, is the so-called guess and check method. Quite often, if our coefficient of x squared is a prime number, well, it only has one way to factor that, and it's just the number times 1. So that basically tells me that either d has to be a and e is 1, or I suppose we could set e equals a and d equals 1, but that's basically just the same thing by symmetry. So one of these coefficients of x in one of these binomials has to be a, and the other one has to be 1. So for instance, that's an example where we might be able to just write in 2 of the coefficients D and E right away, and then pretty easily guess the other 2 M and N, just kind of by a trial and error type approach. And particularly if our constant term is also a prime number, this becomes quite easy, because then of course M times N, my only choice is 1 times prime number. So either in this case, M would be 11, N would be 1, or N would be 11, M would be 1. So when I have very few different possibilities for coming up with D times E equals A, or M times N equals C, when I have very few possibilities, when I have very few ways to factor A or C, a lot of times guess and check can be pretty quick and not too difficult. But there are some times where guess and check is very cumbersome, where there might be a lot of different ways to factor A and to factor C. If A was, say, the number 16, well, that could be like 1 times 16, or 2 times 8, or 4 times 4. That's 3 different unique factorizations. And if C was a number like, say, 18, well, 1 times 18, 2 times 9, 3 times 6, all of a sudden I have like 3 ways to factor A, and then I have 3 pairings, so kind of like 6 total ways to factor C. Like, trying all of these combinations is maybe going to be overly cumbersome. So I would like, in addition to guess and check, if I look at a problem and I think, I think this one's going to be pretty burdensome to go through all of these possibilities, I might want to develop a method, essentially an algorithm, a process where I can say, okay, I can take any trinomial of this form, plug it into this method, and get the result out. So the benefit of having a method like this is, in some sense, it always works. And more or less, it kind of takes about the same amount of time for each problem. The benefit of guess and check is that for some problems it can go really quickly, but for some problems it can go really slowly. So there is an element of strategy here, and that strategy of, is this a good one to use guess and check on, or is this a problem where I'd want to use the AC grouping method on? That comes a little bit with experience, but something we can particularly look for is whether A and C, the coefficient of x squared and the constant term, are prime numbers. If they're both prime numbers, guess and check is probably going to work very nicely. If neither one is a prime number, the AC grouping method might be preferred. If A is a prime number and C is not, I would say it's probably a toss-up. I think most people would go with guess and check, though. So let's look at a couple examples to get warmed up. So here we have a problem, factor 5x squared plus 16x plus 11. And again, remember, I want to factor this into, say, dx plus m times ex plus n, which is d times e x squared plus some stuff times x plus m times n. So to reduce the number of possibilities for d and e, I'm looking for d and e such that their product is 5, the coefficient of x squared. And to reduce the number of possibilities for m and n, I'm looking for m and n such that their product is 11. Well, nicely enough, 5 and 11 are both prime numbers. So d and e have to be 5 times 1 or 1 times 5. M and n have to be 11 times 1 or 1 times 11. At this point, everything is kind of commutative. There's a nice symmetry here. So I'll start by just setting d equals 5, e equals 1. So if I start with this, now I can't just put my 11 and 1 either way here, right? I see that m times n equals 11. I could have m equals 11, n equals 1, or I could have m equals 1, n equals 11. Importantly, I need to look through both of these cases. I can't just slap a 1 in one place and an 11 in the other place and call it done, because I've kind of broken that initial symmetry by placing my 5. I've chosen where to put my 5. Now, basically the question is, does the 11 go with the 5, or does it go in the other factor? Or does the 11 go with the 5, or does the 1 go with the 5? So what do I do? Well, this is where the guess and check part comes in. I say, okay, what if I did this plus 11 and plus 1? And as an aside, these could also be negative 11 and negative 1, like we had discussed last time. But here I could have, say, plus 11, or sorry, 5x plus 1, x plus 11. And if I think of this, what are my cross terms going to be? I'm going to get like a plus 55 plus 1. That doesn't really look like a 16. So I don't really like that ordering. But if I do it the other way, plus 1, plus, sorry, plus 11 plus 1. Well, now my cross terms look like plus 11x plus 5x. That does look like plus 16x. So I think this is going to work. Let me just check carefully. My firsts give me 5x squared. My outsides give me plus 5x. My insides 11x. And last plus 11. This does make 16x. So that's the factorization. So again, if A is a prime number and C is a prime number, there aren't many possibilities. Basically, my D and E are set right away. And then the only question is, for my M and N, does it go one way or the opposite way? More or less, that's the only question. Here I have a situation where A is a prime number, just like before. But C is composite. C is 6, so I could have like 1 times 6 or 2 times 3. So I have a few different possibilities here. Now, again, just like above, I note that I need D times E to equal 5. One has to be 5, one has to be 1 for them to be integers. But now I'm looking for two numbers, M and N. Let me erase this. This is, crowding the space down there. I'm looking for two numbers, M and N, such that M times N equals 6. So I could have M being 1 and N being 6, or 2 and 3. And I didn't mention it in the last example because we didn't need it there, but remember that we could have plus 1 times plus 6 or minus 1 times minus 6. We always want to keep that in the back of our mind. Plus 2 times plus 3 or minus 2 times minus 3. They have to have the same sign to multiply to a positive 6. What is my cross term? What is my coefficient of x? Well, I notice it's a negative. It's a minus 17. So I need some number times 5 plus some number times x to be negative 17, where the sum numbers are either both positive or both negative. Well, if I pick both positive, then I have positive number times positive 5 plus positive number times positive 1. That's going to be a positive number. So since I need a negative 17, I need a negative 17, both have to be negative. If they had opposite signs, I'd have to be extra careful. But here, I need a negative 17. This tells me that both m and n have to be negative. So I basically have four choices. I have -1, -6, -6, -1, -2, -3, -3, and -2. I won't typically write them out like this. It just takes a lot of room. But we notice that the constraint m times n equals 6, along with that cross term being negative, really narrows us down pretty significantly. So we really have four possibilities here, where up here we had 1, 11, or 11 and 1. We only had two possibilities. So this one's a little bit more cumbersome, but probably not too bad overall. I'm looking for negative 17. If I do 5x minus 1 times x minus 6, that's going to give me for the outsides a minus 30. The insides a minus 1, that's minus 31. That's not negative 17. It's not this one. Now, typically we would go through these in our head once we get used to doing all of this. Typically we do it a little quicker, but I'm going exhaustively through them all, just taking care to do it this way while we're getting used to this process. I could have -6 and -1, 5x minus 6 times x minus 1. What is my cross term here? My outsides give me minus 5x, my insides give me minus 6x. That's negative 11x, not negative 17x. So I don't think it's this one either. I could have -2 and -3. So here my outsides give me minus 15x, my insides minus 17x. Hey, that seems to have worked. Right, 5x times -3, negative 15x. And then my insides minus 2x, negative 15 plus -2 is negative 17. And again, we want to go through and carefully check this. We get 5x squared from our firsts. Outside plus inside, again, we just checked that that was negative 17x. And then my last, -2 times -3 is positive 6. So that looks good. So this factors into 5x minus 2 times x minus 3. Okay. Any questions so far? So again, this is kind of the guess and check method, but it's not, it's not a complete shot in the dark guess, right? We're using hints. We're kind of like putting together pieces of a puzzle to really constrain how many guesses we have to make. I don't just start by saying, I wonder if, 4x plus 2 times x minus 1 would work, right? We're using the information that we have to really reduce the amount of possibilities that we have to work through. Okay, and then lastly, let's look at a problem like this. I think we're going to see that this probably isn't a great example for guess and check. I think we're going to see that this is a bit cumbersome. The first thing that I notice is, again, if I wanted ex plus m, or dx plus m times ex plus n. So d times e has to equal a, or 6, and m times n has to equal negative 14. What are my choices for d and e? I could have 1 times 6 or 2 times 3. So right away, I have kind of two completely different structures to work with. I have one possibility that looks like x plus or minus something times 6x plus or minus something. That's kind of one possibility. And I have a completely different structure that's like 2x plus or minus something times 3x plus or minus something. So I've kind of already, in a sense, like branched once to get my d times e equaling 6. And then I'm going to have to branch again, however many times, from the 14. So M and N, this could be like 1 and 14 or 2 and 7. M times N has to be negative 14, so these have to have opposite signs. And it's not so clear here which sign combination we should use. Our cross term is positive, but that doesn't mean that necessarily the positive sign goes on the bigger number, because the bigger number might multiply the smaller coefficient of x and vice versa. So we do have to kind of try them all. +1 and -14, -1 and +14, plus and minus, minus and plus. So I have a lot of different options here. So I suppose I would have +1 -14, -14 +1. Or I'd have -1 +14 +14 -1. I'd have 4 more options for the 2, 7, and then those same 8 would be repeated under the 2x and 3x. We can see this is going to get really cumbersome, right? We can maybe use a little bit of intuition here. So, for instance, pretty much right away, I can see that 14 times 6, that's going to be a really big number, right? That's like, that's over 100 or nearly 100. I don't think that's going to make a 5x. So I don't think having the 14 in this first position is going to work well. The same with having a 7 in the first position. I don't think having the 7 in the first position would work well, because I'm going to get 7 times 6. That seems like that's going to not be a great candidate. I might have to come back and revisit these options, but I think -2 times +7 or +2 times -7 are more promising. If I look at +1 and -14, my outside gives me -14x, inside +6x. That's kind of close, but not quite. That's +8x. Not that one. If I have -1 +14, that gives me, or sorry, the first one was -8x. This one is +8x. That one doesn't look like it's going to work either. This one might work. Let's see. If I do -2 and +7, well, that gives me a 12 and a 7. That seems like that could make a 5. I might have the signs off, but let's check carefully. My outside is +7x. My inside is -12x. Yeah, so I think I got a -5x. So that didn't quite work, but it's close. If I switch the signs, a +2, a +2 with a -7. I think that's going to work. So this is where the kind of guess and check method becomes, again, a lot more cumbersome, where you have to use a lot more time and effort and heuristics, and say, this feels like it's a good possibility, or this feels like it's not going to work, in order to make it efficient. So we would, if we just tried exhaustively, we would have 8 choices for this x and 6x bit, and then 8 more for the 2x and 3x. Here we've got a little bit lucky with a little bit of maybe something like common sense math, along with getting a hit on the third option in the first bit of structure here, the x and the 6x, and not the 2x and the 3x. We got a bit lucky, but you could imagine that in another problem you could get unlucky and have to go down to the 2x and 3x, and then to the last option there. So this one ended up working. And again, if we check carefully, we get x times 6x squared. My outside's minus 7x. My inside's plus 12x. That is a plus 5x. And then 2 times minus 7 is minus 14. So we did get the answer through kind of the guess and check method, but it wasn't easy. So again, what are the differences? What are the things that I notice about these three problems? Not sure what happened to my green marker. Oh, there it is. It got moved. The first problem was pretty easy with the guess and check method. And I noticed that A and C were both prime numbers. They didn't have lots of ways to factor. The second was a little more cumbersome, but still not bad. Here, A was prime and C was composite, but C didn't have a ton of factors, right? There were basically two ways to factor it, 1 and 6 and 2 and 3. And then the one that was difficult is partially because there were different ways to factor A. So I had to have two kind of completely different structures to work under. And then also there were a bunch of ways to factor C. I couldn't eliminate one of the plus minus combinations right off the bat. And C was negative. So I had to keep all of those plus minus combinations. And also C is a composite number. So it could factor as something like 1 and 14 or 2 and 7. So if I see particularly A being a composite number, but also definitely if that's paired with C being a composite number, I'm going to be pretty hesitant to use guess and check. For a problem like this, I would definitely want to use something like the AC grouping method. But for a problem like this, where I see that A and C are both prime numbers, I'm probably going to be able to make pretty good educated guesses pretty quickly and come up with the answer much more quickly than going through something like the AC grouping method. Okay, so let's work through a couple problems. So let's take about 6 minutes or so to go through these. I think similar to the ones we did, the first one should go pretty quickly. The second one might take a couple of minutes, but shouldn't be too bad. And the third one might take a little bit of time. But I think it is good to go through the guess and check method for a more cumbersome one at least once, just to see what that feels like. So if you start in the guess and check method, you might realize what it looks like to go down maybe not the best path. So let's take about 6 minutes for these three problems, and then we'll come back and discuss the solutions. Okay, let's chat about these ones. So I worked through the first two here. For 7x squared plus 50x plus 7, we see that our d and e, our coefficients of x, have to be 7 and 1, right? That's the only way that 7 factors into the integers or into the whole numbers. So we start with 7x in the first parentheses and x in the second parentheses. And then we have to figure out what our m and n are. We know m times n has to be 7, which means we have to have products that look like 1 times 7 or 7 times 1. These have to be the same sign to end up with a positive number from their product. So they have to be both positive or both negative. Since everything in our problem is positive, these numbers are positive and my cross term is positive, then both of my signs have to be positive. So I've got to be looking at +1 and +7. And now the only question is the order. Does the +1 go with the 7x, or does it go with the x? And then does the 7 go with the x, or does it go with the 7x? And I see that if I do 7x plus 1 times x plus 7, my outside gives me plus 49x. My inside gives me plus 1x. That's a plus 50x. So again, pretty straightforward one because a and c are both prime numbers. That made it more easy. It really reduced our number of possibilities we had to search through. For the next problem, 4x squared minus 5x plus 1, this one's a little more challenging because I have two different structures to work with. I could have this factor into 2x in the first parentheses and 2x in the second parentheses that can multiply to give me 4x squared. Or I could have 4x in the first parentheses and x in the second to get 4x squared, right? 4 can factor into 4 times 1 or 2 times 2. So I might be a little hesitant here, but I noticed that the +1 at the end here, that's actually a really easy, I suppose it's not technically a prime number, but 1 is a very easy number to figure out its factors. Its only factors are 1 and 1. So it not only has only one way to factor, but its two factors are even the same. So m and n have to both be 1. They have to be the same sign. So either positive or -1. So I really, again, just have 4 possibilities. 2x plus 1 times 2x plus 1, 2x minus 1 times 2x minus 1, or in the other side of things, 4x plus 1, x plus 1, 4x minus 1, x minus 1. So 4 different possibilities. This isn't going to be too bad because my C is so nice up here, even though my A isn't super nice. So if I try my 2x bit, I see if I put a plus or minus 1 in each of these places, I'm going to get something like 4x squared plus or minus 4x plus 1, and that's not going to work. That cross term, I want it to look like 5x, not 4. I jump to the other structure. I see if I put a plus or minus 1 here, I get like a 4x and an x combining together to give me a 5x. That looks promising. If I put a plus everywhere, that gets me 4x squared plus 5x plus 1. But I want a minus 5x. So I just put 4x minus 1 times x minus 1, and that gets me exactly what I need. If I double check, my first give me 4x squared, that's what I want. My outside minus 4x, my inside minus 1x, so that's minus 5x. That looks good. And then my last -1 times -1 is +1. That checks out. Okay, and then let's go through this last one. So 21, well, 21 has factors of 21 and 1 or 7 and 3. So this is one possibility. This is another possibility. 10 has factors of 1 and 10, or 2 and 5. I know the product has to be positive, so they have to have the same sign. So +1 and +10, or -1 and -10, +2, +5, -2, -5. Now, since these have the same sign, that makes things a little easier for me. I know that if I put in a +1 and a +10, or a +2 and a +5, my cross term is definitely going to be positive here. So I have to have a negative because I'm looking for a negative cross term, right? So these have to both be negative. So that at least helps me a little bit. I can use that one piece of information to reduce the possibilities a bit, but I could have -1, -10, -10 and -1, -2, -5, -5 and -2. Those are 4 valid possibilities for the 21 and the 1, but also for the 7 and the 3. I wonder if I can just copy this. All right, nice. That worked pretty well. It's always a bit of a crapshoot whenever trying to copy something in OneNote, but whoever invented the undo button or Control Z is like my favorite person ever. Okay, so let's think through this. If the 10 hits the 21, that's like 200 something. That's way too big. Maybe I won't write X. I'll just cross it out. So this almost works. I have my outside, so 21x minus 10 times x minus 1. My outsides would be -21, my inside -10. That would give me -31. It almost works, but not quite. 21 times 5, that's going to be way too big of a number, 200 something. 21 times -2, that's going to give me -42. -5, that's not going to work. Okay, so I think I've eliminated this first structure, the 21 and the 1 factors. So let's look down here. If I have the -10 hit 7, that's going to give me a -70. I think that's too much. The 7x minus 10 times 3x minus 1, the -10 in the first factor. Well, that gives me -7 minus 30. That's -37. That's not going to work. Here I have -2 in the first factor, -5 in the second. So that gives me 7 5s are -35. Then 2 3s are -6. That's -41. That's not going to work either. This one might work. -5 and -2. Hopefully it works because it's our last option. My outsides give me -14. My insides -15. Add those together, I do get -29. And if I double check, 7x times 3x is 21x squared. My outsides -14x, insides -15x, that adds to -29x. And then my last -5 times -2 is +10. So that looks good. Again, probably more cumbersome than we would really want to deal with. But we did get the answer. And realizing that both had to be negative really cut our work by about 50% or so. So that was an important thing to notice. Okay, so let's move on to the AC grouping method. So particularly if we see that we have a problem like this, that's probably going to be messy, where I have different ways to factor my A as well as different factorizations for C. If I either realize that, or if I just want, maybe you just want one way to do every problem. And you say, okay, I realize that guess and check maybe for this problem will be a little quicker, but I don't want to have to make the decision of what to use when. I just want one method to do it that'll always work. You could do it this way as well. So before we talk about the AC grouping method, let's just remind ourselves how factoring by grouping worked. So factoring out a greatest common factor, basically. Here I have 5x times x plus 1 plus 3 times x plus 1. And I notice that I have this common factor of x plus 1 in both terms. I can factor that common factor out to get x plus 1 times 5x plus 3. What if I look at this quadratic? Well, 5x squared plus 8x plus 3, I suppose I could go through the guess and check method here and break up a into 1 times 5 and c into 1 times 3 and so on. But another way to approach this would be to look at this as 5x squared plus 5x plus 3x plus 3. So I've chosen to break up my middle term here into 5x plus 3x. I mean, there's nothing particularly wrong with this, right? I could have, I suppose, broken it up as, plus 7x plus 1x, or, minus 6x plus 14x, or something like that as well. But I chose to do it this way. Now let me kind of separate off the first two terms and the second two terms. I'm going to think of the first two terms kind of together, and I'm going to think of the last two terms kind of together. If I think of just 5x squared plus 5x, if I just zeroed in on that and forgot about the other bit, is there any common factor that I can factor out of here? Well, sure, I can factor out of 5. Both terms have a factor of 5. Both terms also have a factor of x. What do I need to multiply 5x by to get 5x squared? That has to be an x. What do I have to multiply 5x by to get 5x? That's a 1. Now let me do the same thing with this second parentheses, 3x plus 3. Again, if I zoom in on that, forget about the part that we just finished. For 3x plus 3, is there any common factor? And yeah, there is. There's a factor of 3. And factoring out that 3 gives me an x plus 1 that's left over. And now I just have my previous problem, right? Exactly my previous problem. I can factor the x plus 1 out, and I'm left with 5x plus 3. I've just shown that I can factor this quadratic as x plus 1 times 5x plus 3. Now, could I have just split this 8x up any way that I wanted and had it work? Well, let's see. What if I did something like 5x squared plus 7x plus x plus 3 and try to do the same strategy? I mean, I guess I can factor an x out of the first two. But these bits don't turn out to be the same. These bits don't turn out to be the same, so I can't do that next factoring step that was so crucial here. I can't do this step. There's really nothing left to do here. So if I can break my middle term up just right, if I can break my middle term up just the right way, like I did here into 5x plus 3x, I can then separate the first two terms and the last two terms. From each of those two sets of two terms, I can get a greatest common factor, and then I can factor again to get my final factored form. And as an aside, I could have There's nothing special about 5 plus 3 being 8. I could have also thought about 3 plus 5. If I factor an x out of the first bit, I do see that I have a 5x plus 3 in both terms. I can factor that out. So I could break my 8 into 5x plus 3x, or my 8x into 3x plus 5x. Either one of those would work, but if I use like 1 and 7 or like 10 and minus 2 or some other, it's not going to work. So what's the goal of the AC grouping? And then one more example down here, or two more examples, sorry. What's the goal of the AC grouping method? Is to figure out how to break this middle term up to make this work, right? We saw that there was a specific way to break this 8x up into 5x and 3x, one way around or the other. And that worked. So how do I know it should be 5 and 3 and not 1 and 7 or not some other way of breaking it up? Well, that's what the AC grouping method tells us. But just to get a little more practice with these, x squared plus 5x minus 3x minus 15. Let's try to do the same thing here. Think of my x squared plus 5x. The greatest common factor there is x times x plus 5. And then my minus 3x minus 15, I can factor a minus 3 out of there times x plus 5. When I'm doing these factorizations, I need to be, number one, really careful about signs, positive or negative signs. And I just need to really be aware that, things could be in different orders, or I just have to be really careful with all of these little details, the kind of bookkeeping elements. But I see now I can factor an x plus 5 out, and I'm left with x minus 3. And then lastly, x squared plus 6x, I can factor an x out of there. Minus 12x minus 72. Well, 12 times 6 is 72. So my goal with the AC grouping method is going to be to rewrite a polynomial that, or a quadratic that looks like this, into a form that's like this, that's amenable to factoring by grouping. So that's the goal of the AC grouping method. So let's do just a little bit of practice on factoring by grouping. We have two problems like the ones I just did, and then a little bit of a challenge problem down here with a cubic. So see if you can work that one out. So we'll take about, let's take about 2.5 minutes for this. I think this should go pretty quickly. It's just a warm up. As an aside, this was the first section in chapter 7. So if you haven't mastered this material, or if this looks really confusing to you, go back to that section 7.1, maybe review that a little bit, work through that homework, practice it a little bit, and then come back to this section and it'll look a little more familiar. All right, so about 2.5 minutes to work through these three. Okay, so looking at these three problems, again, I think these first two are pretty straightforward. Looking at the x squared plus 5x bit, we see there's a factor of x that can factor out of there, leaving us with x plus 5. And then from minus 4x minus 20, the negative 4 can factor out, leaving us with x plus 5. And then we have the common factor of x plus 5 in both of these terms that can factor out, leaving us with x minus 4. So x plus 5 times x minus 4. Pretty similar story in the next one. We get x times x plus 4 minus 9 times x plus 4. Factor the x plus 4 out to x plus 4 times x minus 9. Again, just be careful with the negative signs here. And then for the challenge problem, even though we have higher powers of x, it actually works pretty similarly. 5x cubed plus 3x squared, there's two factors of x I can factor out of there. No constants. And then minus 5x minus 3, I want to make this factor look like 5x plus 3. I need to factor a minus sign out. So I factor out a negative 1 and end up with x squared times 5x plus 3 minus 5x plus 3. So 5x plus 3 is a common factor to both terms. And what's left over is x squared minus 1. Remember, the minus 5x plus 3 is really just the minus 1 times 5x plus 3. So we can even factor something like, say, a cubic, which are typically very, very hard to factor. But if we see this pattern where it works for factoring by grouping, we can factor a cubic pretty easily in this special case. Okay, so let's look at using the AC grouping method now. We're going to start with this problem because, again, it was a pretty simple problem. We worked through this one above with the guess and check method. But let's work through it with the AC grouping method. What's the goal of the AC grouping method? We want to find two numbers, call them m and n, that multiply to AC and that add to B. In other words, I want m times n equals A times C, and I want m plus n equals B. This should look pretty familiar. This kind of just looks like section 7.2. So what's the difference here? Well, the difference is that m and n don't right away give me the factorization like they did in 7.2. M and n tell me how to break up the middle term. Since b equals m plus n, then bx is mx plus nx. I break up the middle term that way into mx plus nx. Then I do my grouping like I did before to get my final factorization. So it's kind of nice that the kind of underlying mathematical structure works the same in 7.2 and 7.3. We find two numbers that multiply to a certain number and add to another number. It has a very similar feel, but that can also sometimes be a downside. If two approaches have a very similar feel, sometimes it can be easier to get them mixed up. In 7.2, when we find m and n, that basically just gives us the answer, x plus m times x plus n. But here, m and n tell us how to break up that middle term, which we then go ahead and do factoring by grouping a couple of times, or factor out of GCF a couple of times to get the end factorization. Okay, so for this particular problem, I see that A is 5, B is 16, C is 11. So I want to find m and n such that m times n equals 5 times 11, and m plus n equals 16. So again, do what I've been doing. I start with the m times n equals number setup, and I make a list of all of my possible m's and n's. Well, 5 times 11, there's also always this kind of hidden factor of 1. So I could have 1 times 55. I could have 5 times 11, or I think that's about it, right? I know the product has to be positive. These have to have the same sign. So plus and plus, or minus and minus, plus and plus, or minus and minus. But I also note that m plus n equals 16, a positive number. So these have to be both positive. So I can actually revise my signs down here and make all of these positive. I can just get rid of the plus or minus signs. Both have to be positive. And I'm looking for an m and n that add to 16. Obviously, 5 and 11. But very importantly, it's not just like, okay, I'm done, that this is x plus 5 times x plus 11 or something like that. This tells me how to break up my middle term. So instead of working with the quadratic in this form, I'm going to choose to make it plus 5x plus 11x. Obviously, the 16 breaks up that way because that was one of our constraints, was m plus n equals 16, then plus 11. And now I can group these first two terms together and the last two terms together. From the first two terms, I can factor out, I guess, a 5x, leave me with x plus 1. From the second two terms, I can factor out an 11 times x plus 1. And then I can factor an x plus 1 out of both of these remaining terms. And that's my answer. Well, let me try to get all of this on the screen at once. I probably want to double check my answer. So my first give me 5x squared, that looks good. My outside's plus 11x, my inside's plus 5x, that's plus 16x, that looks good. My last's plus 11, that also looks good. Looks like a good answer. Let's do 2 more examples. So here I want to factor 8x squared plus 25x plus 3. And again, my AC grouping method is I'm looking for m and n such that m times n equals 8 times 3. This is going to have some additional factors, right? This is going to have more than just a couple ways to factor it. And m plus n equals 25. Remember, the goal is to figure out how do we split up this middle term. So it's crucial to have that the sum of m and n are 25, so we can break that 25x into mx plus nx in such a way that our factoring by grouping will work. Okay, so mn is 8 times 3 or 24. So I guess we could have 1 times 8 times 3, 1 times 24. There's a factor of 2. This would be 2 times 12. 3 times 8. 4 times 6. 5 doesn't work. If I go up to 6, I get 6 times 4. That's a repeat. M times n is positive, so these need to be the same sign. They need to multiply to positive 24. And m plus n is positive. their sum has to be positive, so they have to both be positive. So I don't need to worry about any negative numbers. I can just leave the list as positive numbers like it is here. That's fine. Now I want to consider the second constraint, m plus n equals 25. Well, 6 and 4 is 10, 8 and 3 is 11, 12 and 2 is 14, but 24 plus 1, that is 25. So this shows me that I want to break this up as 8x squared plus 1x plus 24x plus 3. And again, if you had chosen to do 8x squared plus 24x plus x plus 3, that would have worked just as fine. You'd have had a slightly different intermediate factorization, but when you do the second round of factoring and get everything fully factored at the end, you'd have got the same answer. I chose to do it this way because I think it's going to be a little bit easier to proceed, but doing it the other way wouldn't be a problem at all. I group the first two terms and second two terms together like this. My common factor from the first two terms is just an x. And from the second two terms is a factor of 3. And I see this 8x plus 1 is in both of these terms, so that is my factored form. Let's double check. First, give me 8x squared. The outsides give me plus 24x. The insides plus 1, so plus 25x. That looks good. Last, give me plus 3. That looks like the right answer. This one with a having so many ways to factor it, 8 and 1. Well, I guess just 8 and 1 and 4 and 2. 8 has a bunch of different factors, but because they're all the same factor, it makes it a little easier, I suppose. But having a couple different ways to factor it might have made this a bit cumbersome for the guess and check method. But the AC method, is a little more straightforward, is a little more kind of the path is a little more well-defined. Okay, and then let's look at this third example, and then we'll do a couple of practice problems. So again, I have 4 and -5 for A and C. I'm looking for two numbers whose product is -20 and whose sum is B, -9. Because again, I'm looking for how am I going to break this -9x term into the sum of two terms in such a way that factoring by grouping will work. So let's start looking at our factors of 20. We have 1 times 20. We have 2 times 10. 3 doesn't work, 4 times 5. And if we keep going up, we get 5 times 4, a repeat. These have to multiply to a negative number. These need to be opposite signs. I note that m plus n is -9. So the sum has to be negative when I have opposite signs. That means the bigger number has to be negative and the smaller number positive. So minus, plus, minus, plus, minus, plus. So if I look at this setup now, I have all of my ways to get m times n equals -20, where I have opposite signs with the negative on the bigger number and the positive on the smaller number. I need to find one of these that for which m plus n equals -9. does negative 5 plus 4 equal negative 9? No, it equals negative 1. Negative 10 plus 2 is negative 8. That's close, but doesn't work. Negative 20 plus 1 is negative 19, not negative 9. I don't have any choice for m and n that gives me m plus n equals negative 9, and that also satisfies this constraint, and that's, of course, in the integers. So what does this mean? Well, this actually means that this is prime. We can't factor this nicely into dx plus m times ex plus n, where d, e, m, and n are integers. Now, if we had done the guess and check method, this is another downside of the guess and check method. If we had done guess and check, where we're just kind of looking for a solution that seems to work, if we're given a prime quadratic, that can be really hard to discern under guess and check, especially for something like this, where the 4 can kind of break up in a couple of different ways. The -5 can break up in a couple of different ways with different signs and so on. That might be kind of frustrating to check it that way, but the AC grouping method gives us a very nice pattern to follow, and we see that really nothing fits that pattern, so this has to be prime. And let's adjust the problem just a little bit. What if instead of a -5, what if we had a +5? So m times n then would be 4 times 5, or 20. Then m and n would have to have the same signs for their product to be positive. Still m plus n equals negative 9. To add two numbers with the same signs and get a negative, they both have to be negative. Well, now do I have a situation where m plus n equals negative 9? Sure, now this one works. A very small change, just a change in sign on one term, can take a quadratic from being prime, from not being able to factor it, to factoring it pretty nicely. Right here, we would have 4x squared, say minus 4x minus 5x plus 5. This minus 4x minus 5x is how this minus 9x broke down. And we can see pretty clearly factoring by grouping is going to work nicely here. 4x times x minus 1 plus, well, I want this to look like an x minus 1 when I factor it out, so I'm going to choose to factor out a -5 times x minus 1. And then I can factor x minus 1 out from here. Why wouldn't this strategy have worked when I had -5? If I tried to do the same thing, if this was a -5, 4x squared minus 4x minus 5x minus 5, it kind of like almost works, right? I get 4x times x minus 1. I guess I could factor out a -5, but then I get an x plus 1. Or if I didn't factor out a -5, I would get negative x minus 1. I can't get that same factor to pull out nicely. And moreover, it's not just that I chose poorly when I broke into -4x minus 5x. There's no other way that I could break this this -9x apart that would give me a way that I could factor by grouping. Right. So with the -5 here, it's prime. There's no way to factor it by grouping because there's no way to factor it into the product of two linears with integer coefficients. But with the plus 5, when we change this to a plus 5, everything worked out. Okay, so take a couple minutes and work through these three problems again. We start with a pretty straightforward one that we actually had factored before, and then a couple of new ones. So work through the AC grouping method for these. We'll take maybe about 6 minutes or so for these. The first one should go pretty quickly, but the next two you might need a couple minutes to write the list. So we'll take about 6 minutes for these and then discuss them at the end of that time. Okay, let's discuss these ones. So the first one, again, pretty straightforward. We're looking for two numbers, m and n, whose product is a times c, or 4 times 1, and whose sum is -5, so whose sum is b. We see that 4 times 1, or 4, can factor into 1 and 4, or 2 and 2. We need the product to be positive, so they have to have the same sign. And the sum, m plus n, is -5, has to be negative, so both of the signs have to be negative. So -1, -4, or -2 and -2. And I'm looking for a sum of -5. So clearly that's -1 and -4. So I break up that middle -5x into -x minus 4x. I can factor an x out of the first two terms, leaving me with 4x minus 1. And then from my next two terms, I have a -4x plus 1, but I want to end up with something that looks like 4x minus 1. So I factor a -1 out of there, leaving me with 4x minus 1. And then I factor 4x minus 1 out to get x minus 1 times 4x minus 1. That's my answer. So again, the AC method worked well here. Guess and check would have probably worked well here also. This next problem, I mean, this would be a nightmare to do with guess and check, mainly because the number 48 has so many different ways of breaking into the product of two factors. So again, we're looking for two numbers, m and n, whose product is a times c, or 3 times 48, and whose sum is 26. 48 breaks down so many different ways. I actually am going to think through and get a prime factorization for 48. So I have 3 times 48. Well, 48 is an even number, so has a factor of 2. It's going to be 2 times 24. 24 is 2 times 12. 12 is 2 times 6. And 6 is 2 times 3. So I know that 3 times 48 is going to be this product of a bunch of 3s and 2s. I always have a factor of 1, so my first choice for m is going to be 1 times, and then 3 times 48 is 144. If I have a factor of 2, I've used kind of one of these 2's here. Then what's left over? Well, 48 over 2 is 24. 24 times 3 is 72. A factor of 3, well, that's just 3 times 48. A factor of 4, we've used two factors of 2, leaving us with 2 3s and 2 2s, or 9 times 4 is 36. A factor of 6, that leaves us with 8 times 3, or 24. 7, no, I don't see any factors of 7. 8, well, that's 3 2s, 3 factors of 2. So what's left over is 3 times 2 times 3, or 9 times 2, or 18. So 8 times 18. 9, that's 3 times 3, multiplied by 16. And then lastly, 12. 12 is 3 times 4. Leave me with, again, 3 times 4, or 12. And now if I keep going up, 13, 14, 15, 16, I'm just repeating myself. So I'll stop there. Again, these are the same sign because the product is positive, and they both have to be positive because m plus n has to be a positive number. So this is my list, and I'm looking for a line here that adds to 26. That's 8 plus 18. I know this was a decent bit of work to write out this list, but just imagine if you were trying to, if you started with 3x plus something times x plus something, and you were trying to go through all of these and multiply by the 3 and then add the other one and try to figure out which one goes first or second. I mean, this would have taken a very long time to use the guess and check method. So even though this took a bit of time to write out this list, it's kind of a long list. finding m plus n equals 26 was super easy.
I have a quick question.
Yeah, yeah.
So once we find our like numbers for M and N, and then we get to the third step, like that,
Mhm.
yes. So yes, there.
Mhm.
So once we get to like, and we solve the first part where we got like the X and then in the parentheses, the 3X plus 8, is
Mhm.
it like safe to try and like force that into the second problem? Like we know that we have the 3X plus 8. So can I safely assume that that's in the second one and then figure out the numbers?
Yeah, exactly. So that's a great observation, is the whole purpose of going through this whole process is to force factoring by grouping to work. So if I note that when I factor out an x, I see I get a 3x plus 8 factor, I really should expect a 3x plus 8 factor to come out over here as well. So that can really help me when I'm like, okay, 18x plus 48, what factors out of there? Well, I could say, okay, well, I should have a 3x plus 8. So what times 3x equals 18x? That's going to be a 6. And then I just want to check, is 6 times 8 48? Yes, it is. Okay, that looks good. Yeah, so that's definitely a good approach, kind of reverse engineering this little piece here, knowing that I expect the 3x plus 8 and leveraging that knowledge, as long as I'm super careful to check, right? In theory, it would be enough to say, well, 6 times 3x is 18x, so factor out a 6 and we're left with the same thing. And in theory, I could do that without checking, but I might have made an error somewhere along the way here. So I always want to just double check. But exactly, that's a great observation, is instead of recognizing that my greatest common factor here is 6, I can reverse engineer it and say, what times 3x gives me 18x? That's got to be a 6. And I expect the 3x plus 8. Is it true that 6 times 8 is 48? Yes, it is. So I can use that knowledge. I can really leverage that to help me. Yep. Yeah, and then I factor out my 3x plus 8 and I get this.
Okay, I just wanted to double check because originally I
Yeah.
wanted to pull the 18 out and like obviously that would have messed up the whole problem. So
Yeah, in the so 48 is also doesn't have a factor of 18. So if you started
that
down
makes
that
sense.
road, that it's perfectly fine to say, oh, can I factor an 18 out, and then maybe realize, okay, that doesn't work. What's the greatest common factor? It's going to be smaller than 18. So yeah, but that's a good observation though. Yeah.
Thank you.
Yeah. And then I kind of ran out of room for this last problem, so we'll just work through this one from scratch. So here I'm looking for m and n such that m times n is 4 times 25 or 100, and m plus n is negative 20. I'll go through this kind of quick because we only have 2 minutes left. So m and n, I have 1 times 100, 2 times 50, 3 doesn't work, 4 times 25, 5 times 20, 6, 7, 8, 9 don't work, and then 10 times 10. These have to have the same sign to multiply to a positive. They need to add to a negative, so these all have to be negative numbers. And I'm looking for 2 that add to negative 20. That's negative 10 and negative 10. So I break my minus 20x, my minus 20x into minus 10x minus 10x. I can factor a 2x out of here, leaving me with a 2x minus 5. And then I can factor, well, I want to factor the negative out so that I get a minus before the constant. And I can factor out a 5, leaving me with 2x minus 5. And then factor out the 2x minus 5 times 2x minus 5. And hey, look at that. Interestingly, we got a perfect square. So next time when we come back, we will go through a couple more problems. We didn't quite get to these last 3 in the lecture or the work sheet. So I think that's a good a good kind of warm up for next week. When we come back, we'll work through these last couple little problems here, and then we'll also move on to the next topic, factoring special products, where we'll actually see how do we maybe could we recognize this right off the bat as a perfect square and maybe avoids this whole M and N AC grouping business. So that's the plan for next week.